Hello friends, in today's class we'll be solving some numericals based on photoelectric effect. Remember, these are very easy numericals and of course they are the best to fetch marks in your physics exams. So let's get started. Now, before beginning with the numericals, let's take a crux of what photoelectric effect actually is. We'll be summarizing the formulas first and then of course we'll be moving ahead with the numericals. So, firstly, the important formula is E is equals to hc by lambda, which also equals to h nu, where h is the Planck's constant whose values is 6.62 × 10 to the power minus 34 joules second, and c of course is the speed of light, which is 3 × 10 raised to 8 meter per second. Remember, this is the wavelength and this is the frequency. Here this is the wavelength, this is the frequency. Now, well, if you're using a 991 ES calculator, which is most commonly used calculator during your engineering exams, you don't need to worry about the constant values because they are already stored in your const function. So, if this is the calculator, of course it can do maximum of your work. Well, now the overall crux of the entire photoelectric effect stands on this formula, which states that energy supplied equals work function plus kinetic energy. Now, as we discussed already in the theory, this energy supplied equals to work function, the amount of energy that electron will take to just come out of the surface before emission, and then the kinetic energy. So basically, this is the formula. Now, you know that kinetic energy is nothing but as half mv square. This is how you can relate your kinetic energy with velocity. So, the type of questions in exams could be either finding the ES or the energy supplied, phi the work function, or velocity of the ejected electron. Well, as you know, your energy can also be computed in terms of lambda or frequency. So you might also be asked in exam, if X is the amount of the energy supplied, what is the amount of wavelength that you are actually supplying? So basically you need to just relate the above two formulas. These two formulas are interlinked. Well, we'll be solving certain numericals to see the interlinking between the two formulas, so stay connected. Well, before moving ahead, there's an important tip for your exam. This tip is going to help you for your exams. Write the values of constant as a step while solving for the numericals because it has marks. As you know, engineering is a step marking, so these steps also contain marks. But for solving 991, you can use the constant functions. Now, basically, if this is the kind of a question that you are going to get in the exam where lambda value is 1285 and you need to find out the energy in joules, you need to show this step. Well, showing this step is crucial because this step contains marks. So you need to do nothing. You just need to substitute the values of h, you need to substitute the value of c, and you need to substitute the value of lambda. After substitution, don't get into the traditional method of solving. You can use the constants on the 991 ES calculator, and then you can just write the value as it is. So this is an important step which is going to fetch you marks. So don't forget while solving numericals. Now, you know, energy is expressed in terms of joules in SI system. But in quantum mechanics, we use electron volt. So let's understand how to convert joules into electron volt. This is the concept that you need to remember because maximum of the time your energy will be in terms of electron volts, and wherever you will be asked to solve for kinetic energy and velocity, you need to substitute the SI unit values. So now 1 electron volt is nothing but as charge of 1 electron, that is 1.6 into 10 to the power minus 19 coulomb into 1 volt. This becomes equals to 1.6 into 10 to the power minus 19 joules. So basically your 1 electron volt is nothing but as 1.6 into 10 to the power minus 19 joules. Similarly, you can say your x electron volt would thus be equal to 1 joule. Now by using unitary method, you will get 1 joules thus contains 1 upon 1.6 into 10 to the power minus 19. On solving this, you'll get a value of 6.25 into 10 to the power 18. So these are the handy values that you need to remember. Your 1 joule contains 6.25 into 10 to 18 electron volts, and your 1 electron volt equals to 1.6 into 10 to the power minus 19 joules. So basically you can say you need to have a conversion of joules into electron volts. So wherever you are asked to convert joule to electron volt, you will be dividing by E. And of course on the true one, when you will be asked to convert electron volts to joule, you will be multiplying with E. So this is a crucial step you need to remember for conversions. Now let's begin to solve the numericals. The first numerical reads out: find out the threshold frequency and threshold wavelength for a metal whose work function is 3.2 electron volts. So frequency means you need to find the nu value, wavelength means you need to find the lambda value, whereas this 3.2 electron volt is nothing but its work function, which is denoted by phi. You already know that work function is nothing but as energy. Here this energy is expressed in terms of electron volts. Now using the first formula, E is equals to hc by lambda, I can find out the threshold wavelength, and E is equals to h nu, I can find out the threshold frequency. So let's write out the formula. The formula says E is equals to hc by lambda, which is also equals to h nu. So now using the first formula, E is equals to hc by lambda, let's find out the wavelength. Substituting the values, I would say 3.2. Now this 3.2 is nothing but as electron volts, so I'll be multiplying it with 1.6 into 10 to the power minus 19 to get my energy value in joules, which now equals to H, which means 6.62 into 10 to the power minus 34 times 3 times 10 raised to 8 divided by lambda that needs to be found out. This is the lambda to be found out. Therefore, you can say your lambda is equals to 6.62 into 10 to the power minus 34 multiplied by 3 into 10 raised to 8 divided by 3.2 into 1.6 into 10 to the power minus 19. Now, on solving this, you will be getting the value of lambda as 3878 Armstrongs. This is the value of lambda that you will be getting. Now we need to find the frequency value. So we'll be using the formula E is equals to h nu. Again, using the value of E as 3.2, multiplying it by 1.6 into 10 to the power minus 19 to convert it in joules, and then of course 6.62 into 10 to the power minus 34, that's the value for Planck's constant, into nu. On solving, you will be getting nu as 7.7 into 10 raised to 14 Hertz. Now, by using energy, we have seen how to find out the lambda and V. Now, there's an important tip here to remember why it is called threshold. What does the word threshold means here? Well, to understand this, it's important to see which energy are we talking about. Well, if we are talking about the work function energy, then of course the lambda or the nu that is related to the work function's energy will be addressed with the keyword called threshold. Well, this is the energy that is minimum required to get the electron out of the metal surface, and hence the keyword threshold is used for work functions energy. So always in exam, do remember wherever you are asked for threshold keyword, it is referring to the energy that is corresponding to the work function. That's an important tip. You need to remember this while solving your numericals. Now, so far so good. Let's begin with the next one. Here the numerical reads: calculate the velocity and kinetic energy of an electron of wavelength 9800 Armstrong. So we need to find out the velocity, that's denoted by V, and of course the kinetic energy, that is half mv square, of an electron. Now here it is electron. So the mass of electron, which is a constant value, you need to know it is 9.1 into 10 to the power minus 31 kg. And you are given the wavelength of electron as 9800 Armstrong. So this is your lambda. So you are given with the values of lambda, and now you need to find out the energy first. Of course, using the formula E is equals to hc by lambda, we'll be finding the energy. This energy will be nothing but as kinetic energy. So I would be equating this with again half mv square. Now, substituting the values, I would say 6.62 into 10 to the power minus 34 times 3 into 10 raised to 8 divided by 9800 multiplied by 10 raised to minus 10 equals half into 9.1 into 10 to the power minus 31 into v square. And just by using this expression on the left hand side, you will be finding the kinetic energy. Now, so on solving this, first the kinetic energy now equals to 6.62 into 10 to the power minus 34 into 3 into 10 raised to 8 divided by 9800 into 10 to the power minus 10. On solving this, you'll be getting the value as 1.92 into 10 to the power minus 19 joules. Now, do remember, I have taken this kinetic energy not in terms of electron volt, but in terms of joule. The reason to this is always velocity and kinetic energy are generally expressed in terms of electron volts. However, at times you may find kinetic energy in terms of electron volts, but velocity is always being expressed in terms of meter per second, which is the SI unit. So this is the kinetic energy. Now again, half mv square now, which equals to kinetic energy. Therefore, you can say your v is nothing but as under root of 2 ke by m. Just substitute the values. You'll be getting root over 2 times 1.92 into 10 to the power minus 19 the whole over mass, that is 9.1 into 10 to the power minus 31. On solving this, you'll be getting the values as 6.4 into 10 raised to 5 meter per second. So this is the value of the velocity and this is the value of kinetic energy. Now, this is the numerical which usually appears for 2 marks. The marks distribution is half mark, which is 1 mark for this and 1 mark for this. Of course, as mentioned earlier, if you skip this step, you will be losing half mark. Of course, here if you lose this step, you'll be losing half mark. So writing the substitution step is very crucial for solving any kind of numericals in physics. Now, the next numerical, it reads as: when ultraviolet light of wavelength 1000 angstrom is incident on molybdenum, then find the kinetic energy and thus the velocity for ejected electrons. Here you are giving the metal as molybdenum, for which the work function is 5 electron volts. So let's take the given details into picture. We have lambda. Now here you will notice there is no keyword of threshold in front of this wavelength, which means this is the energy that is incident, or this is the energy that you are providing. Now, well, the metal is molybdenum and we need to find out the kinetic energy and of course the velocity, that is V, for the electron. We are given phi as 5 electron volts, the work function. Now, to begin with this, now we know the formula E is equals to hc by lambda. Now, if you see this formula, if you substitute the value of h, c and lambda, you will be getting energy in terms of joules. But now again you need to divide it by E to get the energy in terms of electron volt. So why not to include the same in the formula here? So we'll be dividing it by E here itself. On solving, we'll be getting the value of h as 6.62 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by lambda is given as 1000, which is 1000 to the power 10 to the power minus 10 into E, which is 1.6 into 10 to the power minus 19. Now, as mentioned earlier, you need to write all the values as appearing here during your exams, and then while solving you can just use the constants on your calculator to get a final value. And on solving this on my calculator, I've got the final value as 12.41 electron volts. Now the question would come, how come I knew that I need to convert this energy in the very first step in terms of electron volt? Well, the answer to this is your work function. Now you need to know the main crux formula of this chapter, that stands as energy supplied equals to phi plus kinetic energy. To find the kinetic energy, of course you would want your phi to get subtracted from your energy supplied. Since your phi or the work function is already in terms of electron volt, it would be easier for me to convert my ES in the very first step in terms of electron volts, so that I won't be getting much of into the calculations. Now I be using this formula, ES equals to phi plus KE on solving 12.41 minus work function, that is 5, equals to KE. Therefore KE, of course in terms of electron volts, would be equal to 7.41 electron volts. This is my kinetic energy. But this kinetic energy is expressed in terms of electron volts. So wherever, as said earlier, you are asked to find out kinetic energy and velocity, you would be using SI units. So we'll be converting this kinetic energy in terms of SI unit, that is joules. Now, so to do that, we'll be multiplying it by E. So therefore, my kinetic energy, now in this case in joules, would be equal to 7.41 into 1.6 into 10 to the power minus 19. On solving this, we'll be getting value as 1.185 into 10 to the power minus 18 joules. Well, this is the final value that is expressed in terms of joules. Now, we had to do this in joules even if it is not even asked in the question. The reason is we need to find out the velocity, which is always in terms of meter per second. Now, using the formula, Ke is equals to half mv square. Therefore, V is equals to root under 2 Ke by m. Substituting the values, it's an under root of twice of kinetic energy, that is 1.185 into 10 to the power minus 18 divided by mass. As mentioned earlier, that is 9.1 into 10 to the power minus 31. On solving this, you'll be getting value as 1.61 into 10 raised to 6 meter per second. This is the velocity. So here we are done with the question. We were asked to find out the kinetic energy and velocity. So in the very first step, we found out the kinetic energy, and then we used the kinetic energy formula to find out the velocity. Now, moving ahead with the next numerical. This reads as, wavelength of light incident on a photocell is 3000 angstrom. So this is the wavelength of the light. Again, make a note that it's just the wavelength, there's no threshold word written in front of it. So this is the wavelength of the light that you are incidenting on a particular photocell. So the wavelength of the photocell is 3000 angstrom. So whenever you read the statement as 3000 angstrom is incident on a metal plate, a radiation of X angstrom is incident on a metal plate, make a note in your mind that you are provided with energy supplied. Now, if stopping potential is 2.5 volt, now here comes the picture, a new keyword for you that is of course important, that is stopping potential. Now, what is stopping potential? It's very important to understand the concept of stopping potential. Now, as stated earlier, your energy supplied equals to phi plus Ke. Now, let's take a fictitious example where you are supplying with 100 units of energy, out of which 20 goes for the work function, and you are now left with only 80 units of energy as your kinetic. Here, by using this 80 units of energy, your electron will be moving. Now, you don't want your electron to move, of course. So what you will be doing, you will be suppressing the electron with an equal amount of energy. So if your electron is moving ahead with amount of 80 units of energy, now you would be providing the same amount of energy in the opposite direction to suppress the movement of electron, or to suppress the electron being ejected out. So basically this is what the stopping potential is. So overall, what stopping potential is? Stopping potential is nothing but as the amount of energy that is numerically equal to the kinetic energy which is applied in the opposite direction to stop your electron from being moving out. So this is what the stopping potential. So this is what your stopping potential is. Now, to understand stopping potential in numerical way, it is nothing but as kinetic energy. So wherever you are asked to find out stopping potential, basically you are finding nothing but as kinetic energy. In vocabulary sense, it is considered as stopping potential, but yes, it is just the kinetic energy. Now let's move ahead. The stopping potential is 2.5 volts. Now, make a note, it is not expressed in terms of energy. Now, if it is not expressed in terms of energy, can we subtract 2.5 volts directly from energy? Well, no. You can only add and subtract according to the unit and dimensions. You can only add and subtract based on the same dimensions. Now, since all additions and subtractions are done in terms of energy, you need to convert this into energy. Now, how to convert a volt into energy? Let's say suppose for an example you are given 100 volts. Now this 100 volt would be equal to 100 electron volt for a given electron. So this is the formula that you need to know. Your energy is nothing but as Q into V, where Q is the charge and V is the potential. Now this is the formula that you have already done in your high school classes. Then work function of the cathode of the photocell is what? You are asked to find out the phi or the work function. Now, numerical stands very easy. You are given the energy supplied, you are also given the energy of the kinetic, and now you need to find the difference of energy supplied and kinetic energy to find out the phi. Now, since you already know work function is always expressed in terms of electron volt, we would be finding phi in terms of electron volts. So let's begin. Using the formula, E is equals to hc by lambda. Using the same analysis that we did in the previous question, we know that we need to find out the work function which is expressed in terms of E, and thus we also need to find out the energy in terms of electron volt. Therefore, I would be dividing this by E in the very first step. Let's solve it further. It gives us 6.62 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by lambda, which is 3000 Armstrong. 3000 into 10 to the power minus 10 into 1.6 into 10 to the power minus 19. On solving this, the value that you are going to get is 4.13 electron volt. Well, this is the amount of energy that you have supplied in terms of electron volt. Now, using the generic formula, the energy supplied equals phi plus Ke. So, my phi is nothing but as energy supplied minus Ke, that is equals to 4.13 minus. Now, here the voltage is 2.5 volts. So in terms of electron volts, it would be 2.5 electron volts. On subtracting 2.5 from 4.13, you'll be getting value as 1.63 electron volts. This is the work function that we want. Now, so far so good. Now, let's switch to the next numerical. Here the question reads, radiations of 120 nanometer, make a note, it is 120 nanometer, are incident on the following metal plates having different work function. Identify for which metals the emission will take place. So here we are given 8 electron volt, 10 electron volt, 12 electron volt, and D 14 electron volt. So the question stands very simple. You have radiations of 120 nanometer being incident on a metal plate which the work functions are mentioned, and we need to find out for which metals the emission will take place. So first of all, find out the energy that is corresponding to 120 nanometer incidents. So we will be using the formula E is equals to hc by lambda. Now since all the energies are expressed in terms of electron volt, I'll be dividing it by E to make the formula in terms of electron volt in the very first step. On solving, you'll be getting the value as H as 6.62 into 10 to the power minus 34 into 3 into 10 raised to 8 divided by. Now make sure you are always not given lambda in terms of Armstrong. Whenever you are given in terms of nanometers, make sure the conversion factor is 10 raised to minus 9, and don't get confused with the 10 raised to minus 10 which we normally use. So that could be the step that could be confusing. It's 120 into 10 to the power minus 9 times E, that is 1.6 into 10 to the power minus 19. On solving this, you'll be getting value as 10.31 electron volt. Now, there are many engineering exams in which MCQs are asked. Now, this is a kind of a question that is multiple choice based question. For such question, there is no need to show the working. You can directly do this on the calculator. There's no need to show the working if this is a multiple based choice question which usually comprises of 1 mark. So make sure you don't waste your time by using all the substitutions or presenting all the substitutions on the paper to solve the question. For such type of questions, you can surely use the calculator trick to find out the value quickly. Now, in the question, we got the value as energy value as 10.31 electron volt. Now, this is the amount of energy that you have supplied to the metal. Now, you know what work function is. A work function, let's suppose the value of work function is 6 electron volt. In an example where I'm taking the value of work function as 6 electron volt, it means that the metal would take 6 electron volts for the electron itself to just come out of the surface and just to begin emissions. So any energy above 6 electron volt would definitely make the emission go true. So now I've got 10.31 electron volt as the energy which I have supplied. So it can only kick off the metals whose work function is below 10.31. Now let's suppose if the work function of the metal comes out to be 12 electron volt. Now if the work function of the metal is 12 electron volt, my 10.31 electron volt will make no difference to that metal, and hence that 10.31 electron volt energy would go completely wasted, because 12 electron volt is the minimum energy that an electron requires to get kicked off. So in this case, all the energy which are about 10.31 stands of no use. So cancelling out all the options 12 and 14. Now the question comes about between 8 electron volts and 10 electron volts. Now numerically speaking, even 10 electron volts metal can be used because you are supplying energy as 10.31 electron volts. So this question will have two options as most probable choices, but the best choice would be 8 electron volts. Now why 8 electron volts? Because this is the metal which is on the safer side. Now why this option we have chosen? We have chosen this option as the best choice. Well, this question was asked in Indraprasth University in 2018, where this question was declared as a bonus marks because it was having two questions as obvious choice. So mathematically speaking, even 8 electron volts and 10 electron volts are the obvious answers, but 8 electron volt is the most probable answers. Thank you so much for watching this video. For more content, stay tuned to Ekeeda and subscribe to Ekeeda.